All right, so section 17 is on solving logarithmic and exponential equations. All right, so this is something that should be mostly reviewed for you guys. We did this in Algebra 2. As we do a couple of these, you'll be like, oh yeah, I remember how to do this. Okay, so there are different guidelines for solving exponential and logarithmic equations. There's multiple ways to do the problems. So it says, rewrite the original function in a form that allows you to use the one-to-one property of exponential and logarithmic functions. So you may not know what that means, one-to-one properties. But for example, if you get something like 3 to the x minus 4, or 3 to the x minus 1 equals 3 to the 4, right, what are you able to say? X minus 1 is equal to 4, right? Which gives you x equals 5. Or you could get something that looks like log base 5 of x plus 2 equals log base 5 of 10, which allows you to say, oh, well, x plus 2 then has to equal, or x plus 2 has to equal 10, which means x equals 8. Does that make sense? Okay, so those are the easy ones. When we have things in that form, we can just be like, oh, it says log base 2 of a number equals log base 2 of some different number. These numbers have to be the same. We set them equal to each other. All right, so number 2 says rewrite exponential equations in logarithmic form, or write a logarithmic equation in exponential form. I always say, when in doubt, switch forms. So if you have no clue what to do in a problem, always try to switch forms, and oftentimes that will help you. All right, and then number 3, it says in order to drop a variable that's contained in an exponent, so if you have like 5 to the x or something like that, we take the natural log of both sides. So it says note, you could take any log you want. It's just easiest to be consistent and use the natural log. So a lot of times I'll use natural log, but you could do log base 5, log base 10, it doesn't matter. So for example, if you have 5 to the x equals 4 to the x plus 2, a lot of people kind of panic on those problems. And they're like, I don't know if I should like switch to log base 5 or if I should switch to log base 4, what I need to do. So I just take the natural log of both sides. Because once you have a logarithm, you're allowed to pull exponents to the front. So you can't just pull exponents down like when you don't have a logarithm, right? On the original, if you have 5 to the x equals 4 to the x plus 2, you can't just pull the exponent to the front and say x times 5, right? It doesn't work that way. You have to have a logarithm. All right, so number 1, it says we have 10 to the 2x equals 5. So it says find the exact solution and also find an approximate solution. Okay, so if I have 10 to the 2x equals 5, there's lots of different things that I could do. Okay, if you recognize that you have an x as an exponent, you know you have to have a logarithm. That is why we invented logarithms in the first place, to drop these exponents, okay? So really, you could just take like natural log of both sides, or any log. That allows you to pull the 2x to the front. So I have 2x times natural log of 10 equals the natural log of 5. And I divide over. So I have natural log of 5 over a natural log of 10 equals 2x. So my exact solution would be 1/2 of the natural log of 5 over the natural log of 10. Now, usually if things were on like a standardized test or something and it was asking for the exact solution, what they would want you to do is combine the logarithms as much as possible. So they would actually have you do 1/2 log base 10 of 5. Do you guys see that? Because it's using the change of base formula. The 5 would go to the top, the 10 would go to the bottom. Right, do you guys see it? So it'd really be 1/2 of log of 5. Okay? So that is our exact solution. So if we want the decimal approximation, we just find it on our calculator. Yeah, that base 10 is just the log button, right? So we can do log of 5 and then divide it by 2. So we end up getting x equals 0.349. Did you guys get that? So that's the approximate solution. All right, so what if I have, well, let me do this one a different way too. So you don't have to do things that way. If you don't like to take the natural log of both sides and you really like switching forms, then switch forms. So if you had 10 to the 2x equals 5, right, you could rewrite it. You could say, oh, log base 10 of 5 equals 2x. Do you guys see how I switch forms? Right? So then that means log base 10 of 5, well, that's just log of 5. And when I divide by 2, right, I have log of 5 over 2, or 1/2 of log of 5. Do you guys see how you have exactly the same thing? Okay, it's almost faster doing it that way, actually. All right, so the next one. So I have e to the x equals 16. So we can take the natural log of both sides. And this one's nice because natural log and e are opposite each other. They're like opposite operations, kind of like multiplication and division undo each other. Natural log and e undo each other. All right, it allows us to pull the x to the front, but natural log of e is, like I said, it's 1. It goes away. So we get x equals the natural log of 16. So we find that on our calculator, natural log of 16.
2.773.
Yep, exactly. So we have natural log of 16 is the exact answer, 2.773 is the approximate answer. Really, I should do my little approximate there. All right, so something like this next one, like it's not already set up, so we have our exponential equation. We need to subtract the 4 first, right? So we subtract the 4, so we get 3 to the 5x plus 2 equals 4. And we can take the natural log of both sides. We can switch forms, whatever you want to do. So let's say we switch forms. So we do log base 3 of 4 equals 5x plus 2. Do you guys see? 3 to the 5x plus 2 equals 4. Can you do what? Yeah. All right, so my exact answer is going to be log base 3 of 4 minus 2 equals 5x. So I'm going to have log base 3 of 4 minus 2 all over 5. Okay. So if you do it the other way, and you just take the log of both sides, when you have the 3 to the 5x plus 2 equals 4, and we take natural log and natural log, it allows us to pull the power to the front. So we have 3x plus 2. No, wait, is that 5? Can't read my own handwriting. So 5x plus 2 times natural log of 3 equals the natural log of 4. So we divide out the natural log of 3. And we have 5x plus 2. We're going to subtract the 2 over. And we're going to divide by 5. So what I would do is I would just multiply everything through by 1/5. So that would be our answer. So it looks a little bit different than the other one. Really, with the natural log of 4 over natural log of 3, I would use the change of base. Yeah, Katie?
Is there a reason that you did, like, can you do log as well as natural log?
Yeah, you can do anything. It doesn't matter. Any kind of logarithm. All right, so what is the approximate answer then? Did anybody find it?
Yeah,
Negative 0.148. Did you guys get that? Yeah. All right, so those were all exponential equations. So exponential equations, you can take the log of both sides, natural log of both sides, you can switch forms, lots of different ways to solve, okay? So logarithmic equations. So in order to do this one, I feel like these ones are the easy ones because I like switching from log form to exponential, but I always have a hard time switching from exponential to log. Do you guys feel the same way? Yeah, so if I have log of 3x plus 5 equals 2, that base is going to be 10, okay? So I have log base 10 of 3x plus 5 equals 2, and I want to switch forms. So I do that by doing 10 to the 2 equals the part that was over here, 3x plus 5. So 10 to the 2, we know. 10 squared is 100. So 100 equals 3x plus 5. I subtract the 5 over and get 95. So x is equal to 95 over 3. So if I wanted to find the decimal approximation, I think it's, exactly, you get 31.667. So the exact answer in the decimal form. All right, so this next one's not set up, so we have the log of something equals a number, right? We need to get it in that form first, the logarithmic form. So I'm going to subtract the 2 over. So I'm going to have negative natural log of 3 minus x equals negative 2. Yep, and I divide by a negative 1, so I get positive, positive. All right, so what this really is log base e. So sometimes in Algebra 2, you liked writing it as log base e so you could see what you needed when you switched forms. So if you want to do that, that's fine. So when you switch forms, you have e to the 2 equals 3 minus x. So we have e squared minus 3 equals negative x. So x equals, it would be like negative e squared plus 3, so I'm going to write it as 3 minus e squared. So that's my exact form of the answer. So if I find my decimal approximation, I do 3 minus e squared. E is a number. It's on your calculator. It's where that natural log button is. It's second, and then the natural log button. So we get negative 4.389. So this is where someone in the first class was like, wait, can you have a negative? Are you allowed to have a negative as an answer? Sure. You can have a negative. Just when you go back to check in your original, if you plug in a negative 4 something here, is it okay? 3 minus a negative 4.389? Is that okay? Yeah, you get 7 something, right? Natural log of 7 something, that's okay. So it works, as long as you don't have the natural log of a negative number when you're plugging it in. Yes?
So if we're going to have x, non-calculator function, it would just ask for the exact.
Yeah, if it was non-calculator, it would say exact. And it'd probably be things like that first one where it's like 95 over 3, you know, easy. All right, so next one looks a little scary, doesn't it? There's a lot of stuff going on. This one's actually easier than it looks. It looks pretty scary right now, but it's not so bad. All right, so if we have addition, remember if we have log of A plus log of B, how can we combine those? All right, we do log of A times B. So that's what we're doing here. So we're saying we have log of base 2 of 3 times x equals log base 2 of 5 times x minus 2. Or 5x minus 10 if you want to write that. Okay, so you could do a lot of complicated things. Like in Algebra 2, I remember a lot of people would do this on the test. They would subtract the log base 2 thing over, and then they would divide, and then they'd change forms. You don't need to do that, right? You get the right answer in the end, but it takes a lot of steps. What do we do? Yeah, the log base 2 and log base 2, it's kind of like they go away. We're saying log base 2 of something equals log base 2 of something. Don't say they divide out. People always say, oh, divide by log base 2. That's not what we're doing. All right, so subtract the 5x over. Negative 2x equals negative 10, so we get x equals 5. And then just do a quick check. Make sure that when you plug 5 in, do you get anything that's negative that you're taking the log of? No. So we're good. All right, so the next one, we're going to divide by 2. So I have log base 5 of 3x equals 2. And I'm going to switch forms. So I have 5 squared equals 3x. So I get 25 equals 3x. So 25 over 3 is equal to x. Yep, so if you want to do a decimal, 8.3 repeating. All right, so this next one. So we're going to combine. So we have log of 5x times x minus 1 equals 2. So we have log of 5x squared minus 5x equals 2. So we need to switch forms. So we have a base of 10. So when we switch forms, we have 10 squared equals 5x squared minus 5x. Okay, do you guys see how I did that? 10 to the 2 equals this. All right, so I have 100 equals 5x squared minus 5x. So 5x squared minus 5x minus 100 equals 0. And we can pull out a 5. So I have x squared minus x minus 20. And it does factor. It factors into x minus 5 times x plus 4. So we get x equals 5, and we get x equals negative 4.
Don't you also get x equals 0, but you put out 5?
Nope, because if you set 5 equal to 0, you don't get a solution. If it had been like an x, then you get something. All right, so we have 5 and negative 4. Are either of those an extraneous solution, an extra solution? Right, if you go back and you check and you plug in negative 4, you get negative 4 minus 1, and you can't take the log of negative 5. All right, same with the other one. If you plug in negative 4, you have log of negative 20. So you guys can try, right? If you try to do it on your calculator, it's going to say error. Calculator doesn't like that, right? So it doesn't work. You can't take the log of a negative number. If you remember what the log graphs look like, do you guys remember? They look like this. There was like nothing over here. That's why you can't take the log of a negative number. There's nothing over there. All right, so the only answer is x equals 5. All right, so you might have some weird things. So, you know, pre-calc is always a step up. So you might have some weird types of situations. We're actually going to do a couple more of these, I think, next time, because I didn't do as many as there are. I just did a couple. So this first one says, this is a quadratic type. Okay, we did equations of quadratic type in Algebra 2. We called them W substitutions. So this is like a W substitution. Okay, so what we're recognizing that is W is going to equal e to the x. And if I square both sides, so if I square e to the x, what do I get? E to the 2x, not x squared, e to the 2x. You multiply your powers, right? So what we really have is w squared minus 3w plus 2 equals 0. So do you guys know how to solve something like that? Sure. W minus 2, w minus 1. So we get w equals 2 and w equals 1. But our original equation had x in it. It didn't have w's. Okay, so what we need to do is we need to replace. So we need to say e to the x equals 2 and e to the x equals 1. All right, and we need to solve each of those. I should have put them up here. So if I have e to the x equals 2, how do I solve for x?
You take the natural.
Right, take the natural log. So I do natural log on both sides. So I get x equals the natural log of 2. And this one?
Log of 1.
Yep, what is the natural log of 1? Think about it. Log base e of 1 equals something. E to what power gives me 1?
0.
It's 0. So natural log of 1 is 0. You guys should know that. So make sure you memorize that one. 0. All right, and then you can quickly check if you want to. So you can check, and you will get both of those actually work. All right, so this next one kind of looks like it's the same idea, but it's actually not. Do you guys see what you can do on this next one? Any ideas? Yes, good job. Connor says take out the common factor. What's the common factor? E to the x, that's right. So we're going to pull an e to the x out. So I have e to the x, and I do x squared plus x minus 2. Right, so then we just factor. So we factor into x minus 1 times x plus 2. So I have e to the x equals 0, I have x minus 1 equals 0, and I have x plus 2 equals 0. All right, e to the x equals 0. A number to a power equals 0. Think about 2. Like 2 to the x equals 0. Can you raise anything and ever get 0? You actually can't. So if you had tried to solve this, you would take the natural log. Be like, okay, natural log of e to the x equals natural log of 0. And then you would try to take the natural log of 0. And your calculator would be like, no, don't do this. It doesn't work. So this one doesn't work. So undefined, I guess. But the other two work. So x equals 1 and x equals negative 2 both work. So those are our solutions.
So on the test, are they expecting us to check off to make sure that I'm right?
These ones are okay. It's really the log ones that have issues, like if it has the log in the original. All right, so there's lots of things that we use logarithms for. We talked about a lot of these things last year, like the Richter scale, the decimal scale, anything that has a scale to it, really. So Richter scale, decimal scale, pH scale. Do you guys remember all that stuff? We did little log activities with it. All right, so there's also this thing that's called the law of forgetting. So Ebbinghaus's law of forgetting states that if a task is learned at a certain performance level, then after a certain time interval, the performance level P satisfies log of P equals log of P sub O minus C times log of T plus 1. So I know this doesn't make any sense to you, but basically if you are able to get a 100% on this test, for this chapter 3 test, then in a certain number of months, you're probably not, like without actually studying and so on, you're going to forget some of it, right? That's what it's saying, the law of forgetting. So if you can perform any task at a certain level, if you don't do anything for a certain number of months, you're not going to be able to perform at that level. Okay, and it has to do with logarithms. Isn't that weird that some guy took the time to come up with this? So it says solve for P. So if we have this equation, yeah, we should. All right, and we want to solve for P. what I'm going to do is I'm going to combine the right side of the equation. So it's just like what we did before with combining logarithms. We're going to pull that up as a power first. So we're going to have log of p sub o minus log of t plus 1 to the c. So now what do you think you do? Log of what?
P sub o times t plus 1.
Close. He said times, though. Divided by, right? So it's minus, so you divide it. Equals log of p. Are we able to solve for p then?
Yeah.
Sure. We have log of something equals log of something, right? So we can say p is equal to p sub o over t plus 1 to the c. So if your score on a pre-calc test is 90, what score would you expect to get on a similar test after 2 months? Okay, so t is in months, so t is going to be 2, right, because it says in months here. And p sub o is your original score. Anything with a subscript of 0 usually means at time 0. So your first performance level was 90. And for C is always like depending on the task. It's some kind of constant. So like taking a math exam, I guess, has a C value of 0.2. I don't know how they determine that. I'm sure there's lots and lots of data to find things like that. So we're going to plug it in. So I have P equals P sub O, which was 90, over T plus 1 raised to the C. So I'm going to do 90 divided by 3 to the 0.2.
72.247.
Exactly, 72.247. So it says if you got a 90% on the first test, 2 months later, you're expected to get a 72. Isn't that sad? Oh, why do we have finals? Yeah, that's so sad. All right, you guys can go on your break.